In this video, we're going to learn how to find the electric field of two charged parallel plates. And we're going to find the electric field both between these plates and around these plates. So first, let's set up the problem. So these plates, the top one has a charge density of plus sigma. The bottom one has a charge density of minus sigma. So the top one is positive, the bottom one is negative. They're the same magnitude. And these plates are a distance d apart from each other, and they are infinite in every direction. Now the question is, what is the electric field between these two plates, and how do we find it? So how do we solve this problem? Well, the first step, step one, let's call it, is to recognize that this isn't just one problem. This is two problems. I need to find the electric field of this top sheet of charge and this bottom sheet of charge. And then if I find the separate electric fields for each of those, I can add them together wherever I please. So this isn't actually one problem. This is two separate problems. We've got our upper positively charged sheet and our lower negatively charged sheet, and we can deal with them separately. So the question is now, how do we find the electric field from just one of these sheets? And in physics, this is always a good idea. Try to simplify the problem as much as possible, break it up into its as small of pieces as you can, and then solve those separately. So in this case, because we have an infinite symmetry, so our sheet is infinite in every direction, we can use Gauss's law to find the electric field. And because the sheet is infinite, so if I look at it from the side, there's a bunch of positive charge to the left, and there's a bunch of positive charge, exactly the same amount of positive charge to the right. And so if I'm any point above the sheet, I expect that my electric field will be pointing straight up, because all of the components of the electric field that are pointing to the left and to the right will cancel each other out, because there's just as much charge on the left as there is on the right. So I expect my electric field to be pointing straight up or straight down away from this sheet. So I should use a Gaussian surface that has faces that are parallel to this sheet. And the simplest such shape is a cylinder, so I'll use that. So let's say our Gaussian surface is going to be a cylinder. And let's erase our sheet. So the cylinder is going to sort of straddle the sheet, so half of it is going to be above and half of it is going to be below. And we need to worry about the electric flux both coming out the top from the electric field pointing up and the flux coming out the bottom from the electric field pointing down. And because this sheet is made out of positive charge, I expect the electric field should be pointing away from that sheet. But if you didn't know that, you could assume that the electric field was pointing towards it, and you'd end up getting the same answer, or the correct answer. So let's solve this problem using Gauss's law. Let's start with the relatively easy part, which is the enclosed charge, Q enclosed. And this is just going to be equal to, so because our cylinder is capturing some area, it's the area of the cross-section of this cylinder, we know that it's just the charge inside that area that we care about, which is our charge density times the area. And that's just the area of a circle, which is pi times r squared. So let's say that this cylinder has some radius r to it. And while we're at it, let's say that it has a height h. Let's call this h. Or so the total cylinder height is 2h, so it's got an h above and it's got an h below. Now the only thing we have to find is the electric flux. So remember, Gauss's law says that the enclosed charge divided by epsilon naught is equal to the electric flux, phi e. And the electric flux is just equal to the integral over my total Gaussian surface, let's call that S, the electric field pointing out of the surface. And so for a cylinder, because the electric field is pointing either straight up or straight down, I know that there's none pointing out the sides here. So I only have to worry about the top face and the bottom face. And because the electric field is pointing straight up and the area vector dA is also pointing straight up because it's just pointing straight out of the surface, then E dot dA is just E times dA because they're pointing in the same direction. And this is true both on the top and the bottom because the electric field is pointing straight away from the surface and the area vector is pointing straight away from the surface. So if we want to find the electric flux for our total surface, we need E dot dA of the top one. So let's say area of the integrated over the area of the top surface, E times dA, plus the integral over the bottom surface. Let's call that A bottom, E times dA. But in both these cases, the electric field we can just pull out because it's not a function of x and y. So if we call this x and we call this y, the electric field doesn't change because we have symmetry. Now I'm assuming that the electric fields have the same magnitude at the top and the bottom because we're the same distance away at the top and the bottom. So if I simplify this, this is just the area of the top is the same as the area of the circle in the middle, which is the area of a circle. So E times pi r squared. And we have another E times pi r squared, or just 2 times E times pi r squared. And that's the total electric flux coming out of this surface. So now if we use Gauss's law, we can find that 2 times E, which is times pi r squared, which is our electric flux, has to be equal to sigma times pi r squared. And so the pi r squareds cancel absolutely beautifully, and we get that the electric field is equal to sigma over 2. And this is our final answer. This is the magnitude of the electric field for the positively charged plate. And for the direction, we assumed that it was pointing outwards, and we got a positive answer. So the electric field is indeed going to be pointing out away from the plate. So if this is the plate where this positive charge is located, the electric field is always pointing out away from it. Now, we could do the same exact thing for the negatively charged plate, but it's exactly the same situation. We can set up our Gaussian surface, we can calculate our flux and our charge enclosed. The only difference is that because we have negative charge here, so because we have negative charge on the plate instead of positive charge, our electric field is going to be pointing towards the plate instead of away from the plate. And so the electric field, it's going to have the same magnitude, but instead of plus sigma over 2, it'll be pointing towards the plate, so its magnitude is minus sigma over 2. And so now we can join these two solutions together. So if we're looking at them, if we're looking at the plates from the side, so we see just a sheet of positive charge up here, a sheet of negative charge down here, we know that the electric field for the positively charged plate is going to be pointing away from it, like this. So this is my positively charged plate. This is my negatively charged plate. So it's going to be pointing away from the positively charged plate. And importantly, the magnitude doesn't change as you get further away from the plate. So it's the same on the everywhere on the top, it's the same everywhere on the bottom. And even as you go further down, so as you go below the bottom of the negative plate, the electric field due to the top is still pointing away, and it still has the same magnitude. Now for the negative plate, the electric field is always pointing towards it. So it looks something like this, where I'm drawing here the electric field of the top plate in red and the electric field of the bottom plate in blue. And again, because this plate is infinite, the magnitude of the electric field doesn't change as you get further and further away. So it's pointing towards the plate below the plate, and it's pointing towards the plate above the plate. So it's always pointing towards it as you go further and further away, and its magnitude is the same. So notice that the magnitude of, or the electric field from the bottom plate, if we go above the top plate in this region here, is pointing down, but the electric field of the top plate is pointing up. And because they have the same magnitude, which is sigma over 2, they cancel each other out. So the electric field above the top plate is 0. And it's exactly the same below the bottom plate. The electric field is 0. But between the two plates, the electric fields add up. And so the electric field, the total electric field, let's draw this in, the total electric field is equal to the top electric field plus the bottom electric field, which is just 2 times sigma over 2. Or sorry, 2 epsilon naught. There's an epsilon naught in the bottom. Or sigma over epsilon naught. So this is our final answer. The electric field is 0 everywhere outside the plates, and it's sigma over epsilon naught in between the plates. And I think up here I was also, yes, I was also missing an epsilon naught. So there should have been an charge enclosed divided by epsilon naught. That's Gauss's law. Finally, I'd like to thank all my patrons on Patreon. Your support is greatly appreciated, and it is you who makes these videos possible. If you aren't currently a patron, to get early video access, behind-the-scenes footage, exclusive content, and join a like-minded community, click the link on screen or in the description below. Thanks for watching.